Hello everyone, welcome to Lunch with Larry. Today we're going to talk in our second of a series of 4 about design control. Today's topic is systems modeling. So we're going to discuss functional relationships between the different components of the system and how to build that into our requirements management set. The first thing to talk about really is me. I just wanted to drop some information about me. Our design control registration link, if you want to give that to somebody to view some of this series, or our YouTube channel. If you get the chance, please subscribe. So again, today we're going to talk about this circle of capabilities where we have requirements management as the core, systems modeling is our definition of good or positive definition of the design. What does the system need to do? So requirements is the first, systems modeling is 1B, standards management, external standards management. How do we get that external view of standards into the requirement set? Verification and validation, what is our evidence that the device complies with our definition of good? And finally, our negative view of the design, which is risk management. How do we assure that the device doesn't do certain things? So let's just jump right in. So when we talk about systems modeling, what exactly do we mean? And I'm just going to start with a black box transformational model where we have inflows to the function transforms those inflows into the outflows. The inflows, of course, are outflows from other functions. So this is a chain of functions that are put together that are used to describe what is this transformation, and not only what is the transformation, but what is the characterization of the outflows that assure that the function or this transformation is operating properly. So that's really what we're trying to define here is how do we know that the function works? How do we know that it does what we say it's going to do? So what is that function? It's a verb-noun combination. So essentially it delivers vacuum, regulates pressure, gets a configuration, lots of different types of functions depending upon the discipline that we're trying to deliver. So if the function is deployed in a component of the system that is a mechanical design component or a software design component, obviously the way we describe those functions is different. But essentially it works the same way, inflows, outflows, and requirements. In this case, we have this regulates pressure function. So we then have the transformation, and maybe the inflow to this function is 120 psi line pressure at 20 CFM. So we have an inflow, and that inflow also is paired with a control inflow. So maybe we have an 8-bit pressure level that is being communicated into the function as well. Now, this outflow then might be regulated down to something like 40 psi plus or minus 1 psi. And in this case, the requirement then would be that the pressure regulator provide an output or an outflow of 40 plus or minus 1 psi at a minimum of 5 CFM. So this is just an example that if I had a pump and the pump was the lowest level component in the design, I could use this function to define what it is this pump is going to deliver. Now, one of the problems that you run into in a design is, let's say we're doing risk management. And one of the designs I worked on in the past is a system that fixates the eye. And in that case, it would be vacuum that we're trying to deliver. Well, we identify the fact that if we put too much vacuum on the eye, we rupture the globe. So we have a much higher risk than we originally had anticipated. What we want to do then is sort of deepen the level of our understanding of our control of this regulating pressure function. And in this case, what we're going to do is we're going to build it out into a subsystem so that we get better control. So now we might have a printed circuit board, a proportional valve, a pump, a pressure sensor, different components that give us that closed loop control. And each one of those components then have a set of functions that are associated with it. But at the high level, we're still delivering pressure, but we might be delivering pressure at a much more granular level or a much more controlled level. And what we need to do is provide this internal control to our pressure system to assure that we don't get this risk that we've identified. In that case, it's also a verb-noun combination. We're delivering vacuum again, but the chain delivered by inclusion of the functions in a group is the important aspect of this now. So instead of just having one function that says we're going to do it all, what we have is many functions that are delivered in a chain in order to give a system level result. So I can say that an individual function is delivered in a printed circuit board or a proportional valve, but what I'm concerned about for the overall system is delivery of the pressure as an output of the functional chain, not of any individual function. Now, these functions go across multiple components of the design and therefore multiple disciplines. So we can't think of systems level requirements as something that's characterizing a single discipline. It's not always, but very often it's going to be delivered by multiple disciplines. So got to kind of think about it like that. It's going to transform again the inflows into outflows. And in this case, now we have this this 120 psi inflow, and an integer that defines the derived pressure, and the outflow now is going to be something of higher control. So maybe in this case, we want 0.5 psi as the outflow and some other idea of control. So we might have a more granular psi, we might also have a higher or lower pressure, different things that we want out of this subsystem than what we wanted before. So now we have this outflow of the overall system that is more granular. Now, if you look at this, each one of these functions that are delivered by the different components of the system, the outflows are different than what they were when we were just talking about the pump. So the printed circuit board might have a 0 to 12 volt DC output. We might have an actual pressure that comes out of the pressure sensor. So it's actually telling us what the actual pressure is in an ASCII format. So when we break it down in this way, the outflows of each one of those functions is very different than what the outflow of the overall system is. And I think a lot of times when I've talked to people about how to do systems requirements work, the way they think about those system requirements is sort of a pass-through. They'll write the requirement at the system level, and then they think that the design level delivers the same thing. And that's never the case. When we think about chaining together functions across multiple components of the system, those functions at the design level are delivering something very different. I think you can see that from this diagram. So what we want is a deconstruction of that allows us to trace the system's functional chains to the system's requirements and each individual function outflow to design requirements, so we understand better the delineation between what the functional chain delivers and what any individual function delivers, if that makes sense. So what is a product capability? Capability is what the device does at a high level, defined by one or more functional chains. So it's very common you're going to have multiple functional chains that are delivering that particular capability, and that capability's traceability is really to the user needs. And what I'm trying to do here is help you to understand the data construction in systems modeling and how it relates to the requirements in the requirements management solution. So the functional chains are going to be realized by one or more system requirements, and the individual functions by one or more design requirements. So this is really what we're trying to do from a traceability standpoint between the two systems. Typically, what you'll see in industry is the requirements management solution is delivered in ALM, the outputs are delivered in PLM, and then the functional models are delivered in systems modeling applications. And so the one I'm most familiar with is systems modeling Workbench, which is kind of like GitHub is a wrapper around open source Git. Siemens SMW is a wrapper around Capella, and Capella, it delivers the Archadia method. One of the really nice things about that particular tool is it's built around a method. It's not just a bunch of diagramming tools. It's a method for doing decomposition of the design, which we're going to talk about here in a second. But that traceability between those two systems is done across an interface typically. So this is really what we're looking for. Capabilities to user needs, functional chains to system requirements, and functions, individual functions to design requirements. So this Archadia method, what we do here is we decompose the design starting at this operational analysis level. So at the operational analysis level, what we're doing is we're expanding our view to everything that's included in the design space. So if I'm going to do a ventilator, I'm thinking about the hospital, I'm thinking about patients, I'm thinking about clinical staff, all the things that need to be done to deliver ventilation. That's the first step of the design. Do I understand what I'm trying to do for users and how I'm going to deliver those aspects of the system? The second level is the systems level. And what we do there is we separate systems, what we're going to actually deliver, what we're building from the rest of the system to understand what goes in the design that we're putting into the field and what exists outside the system. And I'll provide some examples of that. But then we go to the logical architecture. We're going to deliver this as we're going to have a venturi, we're going to have a pump, we're going to have a controller, but we're not saying specifically what kind of controller. We're just logically, this is the way we're going to break the system down. Then when we get to the physical architecture, we're going to deliver this function in this PCB. We're going to deliver this function in the sterile nurse, for example. So the physical architectures, we're down and we actually know what the design is. So this capability diagram is the first aspect of that, where we're saying in the design space, what are some of the things that we have to do? We have to connect to the patient. We have to deliver ventilation. We have to notify of operational issues, that kind of thing. And so in that case, what we're going to do here is we're going to take that capability that is deliver ventilation, and then we're going to break it down and we're going to fully define it. So that capability then includes a variety of other capabilities. We're going to have a patient assist control mode. We're going to synchronize mandatory ventilation. We're going to do all kinds of things that are related to delivering ventilation. Once we understand better at the top level, everything that's related to that deliver ventilation capability, what we're going to do is we're going to break it down. The first way for us to do that is what's called an OAB diagram, operational activity diagram. Blank is what the B stands for. And we're going to identify the steps that someone would have to go through to deliver that particular capability. Now, in this case, what we have is the purple line, the blue line, and the green line. Those are all related to these chains that are on the right side over here. These are what's called functional chains. And as we go through the levels of the design, as I discussed before, we're going to provide more and more detail as to how these activities affect the different components of the design. So in this case, we then have this deliver ventilation defined as a activity diagram or an activity chain. And now we're providing more detail on the steps that are going to be required to deliver that ventilation. Okay, so now we're going to go down to the systems architecture level. And what this does is it takes this middle box is the ventilator. This is actually the box that we're delivering. And of course, we're going to have a variety of different functional chains here. And now we're providing much more detail as to how this thing is going to be delivered. One of the things I like to talk about here is this monitor patient vitals, this blue line. And up in the top right here, we have this box that says to deliver patient vitals. I think this is a good example of why we do this diagram. So let's just say we want to measure pulse oximetry. We want to know the patient's oxygen levels. Well, in this case, what we're saying is the clinician is going to monitor all of the vitals, and those are going to be done outside the system that we're delivering. So what if we wanted to then have a function that is monitor pulse oximetry, and we wanted to deliver that in the ventilator box? If that were the case, you can imagine that function would be broken out and then it'd be interrelated with the rest of the logical components of the system so that we know what to do with that data when it was done. Is it going to be used in an algorithm? Are we going to make any automatic adjustments to the system based on the functionality? How is it going to be related to the ventilator software? All those questions have to be answered if we put it in the box. And you can imagine the risk of delivering monitor patient vitals in a clinician is very different than the risk that would be in delivering it as a ventilator. If it's a person, it's largely going to be controlled with labeling and training. If we deliver it in the system, we might have validation activities that are associated with assuring that the algorithm provides the output that we expect, for example. So that's the purpose of this whole exercise, is to get to a place where we've taken the entire design space and now we've separated literally what's in the box and what's out of the box. And that's really what the purpose of this whole process is. Okay, so now we have this deliver AC mode. Deliver AC mode is part of delivering ventilation. So we're going to take this functional chain that is the green functional chain, and we're going to further decompose it. So now we're at the logical functional level, and we now get a whole bunch more detail. So the blue functional chain is delivering the AC mode, and now we have valves, we have sensors, we have double circuits, we have housings. And one of the things I kind of like to mention here as we go along, now we have a pretty good definition at the logical level. We're getting closer to this physical representation where we're going to start saying, okay, we're going to deliver certain functions with people in the system. Now, if you look at the 62366 medical device usability document, you're going to find that this diagram looks a lot like the diagrams that they show in usability. And one of the things that you need to think about is when we do usability engineering, what we're doing is we're looking at this function that's delivered by a person and the place in the system that it's being delivered to, and we're assuring that the function that we think the user is delivering is actually going to give us the expected feedback to the system at the user interface in the system, whatever the user interface is, whether it's a touch screen or buttons or whatever. So this provides us with a really nice map of what to analyze when we're going into this usability analysis. And I think this kind of a diagram is sort of typically kind of lacking when we go to do this kind of development work. We don't have this granular view of who are these different users in the system and exactly what are they delivering to the system and at what point are they delivering it to the system. So we have this usability FMEA structure to operate off of. I think it's very important. Okay, now we're down at the physical functional level. You can see there's a ton more detail here. We have the different aspects of the system. We have the turbine and how it's delivering it. And the deliver AC mode, again, is this blue functional chain. And it goes through all kinds of different components of the system. It goes through the ventilator software. It goes through the CPU. It's going to go through the turbine central control PCB. And it's defined by these design requirements that are the outflows of the functions. So the blue line that runs out of the turbine that has the arrow that's associated with it, this design requirements level arrow here. The design requirement characterizes the outflow of the function as it's delivered in one component of the system. What you can imagine is the system requirement, though, delivers this functional chain that goes across multiple components of the system. And I think from an illustration standpoint, you can see that what's delivered by the overall system is dramatically different from what is delivered as an outflow from the turbine function. So this is really an illustration of how this system model needs to be constructed so that we understand clearly the definitions and the differences between these different artifacts in the requirements management solution. So if we roll over to the requirement set now, we have this function that's generate airflow. That function is then decomposed by a set of requirements, and we write the requirements as outflows of each one of the functions. So how do we know that we're done with the requirement set? We know we're done with the requirement set when we've written at least one requirement against each one of the outflows of that particular function. So when am I done? This is what I was saying a minute ago. The answer is when we get done with characterizing each one of these functions that are defined in the system. So what's the value? Why should we go to this kind of effort? What's the point of all this? Yeah, I ever had that gnawing feeling? So when I do requirement sets, you want to feel like you have control over how the system's defined, that everything has been done. And when I finish with this set of requirements where I haven't built the functional model first, I always have this gnawing feeling that I'm missing something. And I think this goes a long way to providing a formal definition of what needs to be constructed. And that, to me, provides me with a much better sleep at night. And it also helps me to understand formally how the device works. So one of the things I've said in the past is in projects that I've worked on is we really don't understand how this device functions. And then I get a lot of pushback, right? So, well, of course we know how it functions. Well, what I'm talking about is a formal understanding where I have diagrams that describe the relationships between all of the functions and how the different requirements affect the rest of the system. That kind of a formal understanding, very few people have in their device. They just don't understand how the different aspects of the modeling can affect other parts of the system. To me, this is really what a complete set of requirements means. It's really important also when we go back and make a change to the device later. So we identify a risk in the field, we look at our risk management system, we do an impact analysis. How do we know that we've fixed the problem? And I think if we don't have the implication of a function built into the system, one of the things that I think is really important in this whole process is functions oftentimes serve more than one functional chain. And those functional chains sometimes serve different user needs. If we don't really understand how the functions and the different components of the system interrelate with all of the different activities that are going on with the device, when we make a change to a function or an outflow, we might miss the fact that it serves more than one functional chain, which serves more than one user need, which might mitigate more than one risk. So we really need to understand this better so that as we do our analysis of these different requirements and the problems we've identified in the field, we understand the implication of it and we can make a change that doesn't break the system. Yeah, and this elimination of requirement subjectivity, I think, is really important. So if you need any help with integrating system modeling with your requirements, how to develop systems models, how those requirements are related to it, and redefining your requirements going forward, be happy to help with that. And again, this is me. Anything that you need from just a chat about what you're up to you have some specific need about developing systems models or purchase of systems modeling programs, requirements management programs, applications, I'd be happy to help. So please feel free to give me a call. So thanks so much for our second session, and I look forward to our next time.